Astronomers just found a mysterious object at the edge of our solar system, and its orbit breaks all the rules. Could this strange discovery disprove the existence of Planet 9, or reveal something even more bizarre? The solar system is defying expectations. Its unusual orbit raises critical questions about the hidden ninth planet theory. This isn't about spectacle. It's about precision and data. Watch this video to learn more about Ammonite's surprising path and what it could mean for our understanding of the solar system. In 2023, astronomers using the Subaru telescope in Hawaii spotted something unusual, a faint, slow-moving object drifting against the backdrop of distant stars. It wasn't just another icy fragment beyond Neptune. This one had a story buried in its path. Part of the Fossil Survey, a project aimed at mapping the solar system's most remote icy bodies, the object was officially designated 2023 KQ-14. Initial data hinted at an extraordinary orbit. Follow-up observations by the Canada-France-Hawaii telescope in 2024 confirmed it wasn't a typical trans-Neptunian object. Researchers dug into archival images going back nearly 2 decades, and there it was, quietly tracing its arc through space since at least 2005. It travels in an elongated loop around the Sun, swinging in from about 66 astronomical units, AU, and drifting as far out as 438 Australian dollars, well beyond Pluto. One full orbit takes nearly 4,000 years. This trajectory places it in an exceptionally rare category of objects known as cedoids, distant, detached bodies that don't come close enough to be influenced by Neptune's gravity. Before Ammonite, only 3 were known: Sedna, 2012 VP-113, and 2015 TG-387. Yet it doesn't just expand that list, it complicates it. What truly caught scientists' attention wasn't its distance, but its unexpected orbital angle. Unlike the others, its path points in a different direction, hinting at a gravitational history that doesn't match the rest. The discovery of Ammonite reopens a debate that has captured the attention of planetary scientists for nearly a decade, the Planet 9 hypothesis. The theory proposes that a large, yet undetected planet somewhere between 5 and 10 Earth masses is lurking in the outer solar system. Its presence has been used to explain why several distant objects appear to be gravitationally aligned, their orbits clustered in a way that doesn't seem random. This idea gained traction in 2016 when astronomers noticed that 6 or more extreme trans-Neptunian objects, TNOs, including cedoids, shared similar orbital characteristics. The simplest explanation was that something massive was shepherding their paths. But Ammonite doesn't follow the expected pattern. Its orbit is misaligned, and in some simulations, even anti-aligned, when compared to the other cedoids. This means that instead of pointing in the same general direction, it orbits in the opposite direction, breaking the symmetry that helps support the idea of a common gravitational influence like Planet 9. To investigate further, Dr. Yukin Hang and colleagues at the National Astronomical Observatory of Japan modeled the object's orbital evolution. They found that its current trajectory has remained stable for billions of years, suggesting it hasn't been disturbed recently. More importantly, the orbit never matched that of the other cedoids, not even in the distant past. One possibility is that Planet 9 simply doesn't exist, and the apparent clustering of previous objects was due to observational bias or chance. Ammonite's orbit raises important questions about the early history of the solar system and the forces that shaped it. With only 4 known cedoids, the sample size remains small, but it adds a valuable layer of complexity. Rather than confirming existing theories, it encourages astronomers to re-examine alternatives. Several scenarios are now being revisited. A stellar flyby during the early stages of the solar system could have disturbed outer objects, stretching their orbits without requiring a Planet 9. The Sun may have captured foreign objects from nearby stars during its formation in a densely packed stellar nursery. Or a rogue planet, one that passed through or originated in our system, may have shaped these orbits before being ejected. Ammonite's orbit appears to reflect one of these ancient large-scale processes. Its detachment and long-term stability indicate that whatever shaped its motion happened very early, perhaps even during the solar system's first 100 million years. This is where upcoming surveys become critical. The Vera C, Rubin Observatory, set to begin full operations with its Legacy Survey of Space and Time, LSSD, will likely discover hundreds of distant objects in the next decade. With that many orbits to study, astronomers will be able to identify whether the clustering pattern holds or dissolves in a larger sample. In the meantime, objects like Ammonite serve another purpose. They help define the boundaries of our solar system, not just in terms of distance, but in terms of the gravitational reach of the Sun and its planets. Astronomers are eager to uncover its secrets. Is it ice-rich like Pluto? How does it reflect sunlight? Its composition could reveal whether it formed here or was pulled from another region. Every discovery helps us understand the true nature of our solar system's evolution. Ammonite may not solve the Planet 9 mystery, but it's a game-changer. Its unique orbit challenges existing models, reminding us that science is all about questioning, revising, and exploring new data. As we discover more, it could reveal hidden forces shaping our solar system in ways we have yet to comprehend. The cosmos, after all, often hides its deepest truths in the quietest corners, places where objects like Ammonite drift silently for millennia, carrying with them the fossilized clues of cosmic history. With each new discovery, astronomers are not just adding dots on a map. They are decoding the story of the solar system's birth, evolution, and potential future. Understanding these distant, detached objects isn't just an academic exercise. It has practical implications for how we view the architecture of our cosmic neighborhood. If these extreme trans-Neptunian objects, ETNOs, are more common than we think, it might indicate that the solar system's outer edge is far more structured and possibly more crowded than previously imagined. They could trace the outlines of unseen gravitational influences, not only from proposed planets, but also from historic cosmic events that left their mark on orbital dynamics. Future missions may aim to send robotic probes toward these distant bodies, much like how New Horizons revolutionized our understanding of Pluto. While Ammonite lies much farther than Pluto, making a direct visit a formidable challenge, it still sets a precedent. If we could design spacecraft capable of faster transit speeds or gravitational slingshots using giant planets, then perhaps in a few decades, a probe could reach one of these cedoids. A close-up examination would not only reveal surface composition and geological features, but might also unlock new theories about icy body formation in distant regions of the solar system. Meanwhile, simulations continue to play a pivotal role in understanding the nature of objects like Ammonite. Advanced modeling allows researchers to rewind and fast-forward time, visualizing how orbits might evolve over millions or billions of years. These simulations reveal the intricate gravitational ballet playing out across the outer solar system, one influenced by massive planets, galactic tides, and even the faint push from the collective mass of stars in our Milky Way. Some theories even suggest that a distant planet like Planet 9, if it exists, may have been a captured object itself, perhaps a rogue planet once ejected from another solar system and drawn into our own during the chaotic days of planetary migration. If such a body lurks in the deep, cold dark, it may not resemble any of the gas giants or ice giants we know. It might have a completely different atmospheric composition or an unusual internal structure shaped by alien origins. Detecting it directly remains a challenge, as its vast orbit means it reflects very little sunlight. But new infrared telescopes on the horizon could help detect such a faint signature. In the coming years, sky surveys will generate terabytes of data every night. Artificial intelligence and machine learning tools are increasingly becoming essential in sifting through this deluge of observations. Algorithms trained to recognize subtle movements against the starry backdrop could spot more ETNOs, cedoids, or even interstellar visitors like Oumuamua. These tools not only accelerate discoveries, but also reduce human error and observational bias, potentially unveiling patterns we never noticed before. The broader cosmic context is equally fascinating. Our solar system is not an isolated entity. It moves through the galaxy, occasionally interacting with gravitational forces from passing stars or dense molecular clouds. Such interactions, while rare, could drastically reshape the orbits of outer solar system bodies. They may even explain anomalies like Ammonite's strange inclination or the erratic orbits of other detached objects. Understanding this connection between the galactic environment and local orbital mechanics could provide a unifying theory that links the microcosm of solar system dynamics to the macrocosm of galactic evolution. Educationally and philosophically, these discoveries challenge how we define the solar system's boundaries. Traditionally, textbooks in the map at Pluto or the Kuiper Belt, but objects like Ammonite suggest the true boundary is much farther, possibly extending to the Oort cloud, an invisible shell of icy bodies nearly a light-year away. In this vast, dark expanse, the sun's gravity still has influence, albeit faint. Ammonite is a reminder that the sun's reach is broader than we often realize, and that its gravitational fingerprint extends deep into the unknown. In essence, Ammonite is not just an object. It is a messenger from the edge, whispering secrets about the forces that shaped our solar system. As astronomers prepare for the data revolution brought on by new observatories, the groundwork laid by discoveries like Ammonite becomes even more vital. They act as signposts, pointing toward areas of sky and epochs of time that deserve closer attention. As we continue to probe the shadows of our solar system, we're not merely searching for missing planets. We are rewriting the origin story of our celestial home, one orbit at a time. Hit that subscribe button, share your thoughts below, and let's keep exploring the together. Thanks for watching, and we'll see you in the next.